So in the previous lectures, we discussed about slew rate. So I thought for the first 5 minutes, we'll quickly brush through that. And then we'll start analyzing different problems on offset and gain. Okay. Yeah, we'll discuss the impact of offset and finite gain on both amplifiers and frequency dependent circuits like integrators and differentiators. So first, you are given a waveform like this. This happens to be the waveform of at the output of a amplifier circuit. So now a question was asked, can you, by looking at the waveform, say, assume that this is an inverting or a non-inverting amplifier. Okay, there is no frequency dependence in the circuit, but the op-amp is non-ideal. By looking at this waveform, can you say whether it's slew rate limited or bandwidth limited? What can you gather from this waveform? Is it slew rate or bandwidth? See, remember, whenever you are bandwidth limited, if you feed a step input, you should get what kind of a response? An exponential first order response. But this looks like a ramp, right? It's just linearly increasing. And when will you have a linear increase? When you're slew rate limited. So this is actually a slew rate limited output, right? If your output is increasing linearly, once it hits here, so that's what I've shown here. If your output is changing, just an idea that your output is changing, the green is the output, so then it's slew rate limited. Bandwidth generally should look, let's take an example like this. So I've used the same color for input and output. Let me say it looks like this. So now here you can say that it's bandwidth limited. Okay. So when you feed a pulse signal, you should see a first order rise and a first order fall. So this is a first order exponential rise and an exponential fall. When you see that, you know clearly it's a bandwidth limited system. So you will see such kind of waveforms. If you feed a stream of digital data, for example, your wireline connects your hard disk to computer, or if you actually can plot those waveforms on an oscilloscope, it will look, a badly designed cable will produce a waveform like this. If you transmit a stream of bits to a cable can be modeled as a finite bandwidth system. And if you transmit a stream of bits, and if the bandwidth of this cable happens to be very low, then you will end up getting a first order rise and first order fall like this. Okay. Since both of you are from EEE and ECE, you must have heard of a word called intersymbol interference, no? A finite bandwidth causes what you call as intersymbol interference. So that's it. So now we'll come back to the actual discussion of today's lecture, which is the impact of op-amp non-idealities on amplifiers and frequency dependent circuits. Say you're given a circuit like this. It's a non-inverting amplifier, and it turns out you're using a non-ideal op-amp whose DC gain is 60 decibels. Whose DC gain is 60 decibels, and the gain bandwidth product is 10 megahertz. Your goal is to find out what is the maximum gain of the circuit. Okay, which happens to be at DC, right? So generally for any op-amp based circuit which is frequency dependent, if your op-amp gain is frequency dependent, the gain always happens to be maximum at DC. So let's find what is the DC gain of this circuit. Can you guys try this? It's given that DC gain of this entire amplifier circuit. It's given that the op-amp's DC gain is 60 decibels. So try this one. Try solving it, and then I'll quickly explain it. So whenever you're given in a non-inverting configuration, it's very easy to analyze. What is the feedback factor for the circuit? What is beta for the circuit? Can I say it's close to 1 over 10 power 6? Because it's R by R plus 10 power 6. Yes, close to 1 over 10 power 6. Okay. Now, keeping this in mind, can you say what will be the closed loop gain in negative feedback? Let's assume the system is in negative feedback. what is the closed loop gain of the system? It's given that the op-amp's DC gain is 60 decibels. 60 decibels means in volts per volt unit, it is 10 power 3. The gain is 1000. If the DC gain is 1000, you can quickly estimate what will be the closed loop gain. It's a non-inverting configuration. So you can see that it will be A by 1 plus A beta. And what is A beta? No, calculate it. What is A beta? A beta is simply 10 power 3 upon 10 power 6, which is 10 power minus 3. So your loop gain is negligible. It's almost much smaller than 1. So therefore, the closed loop gain of the system is A itself. A by 1 plus A beta. And A beta happens to be very small, right? It's close to 10 power minus 3. So what is happening here is that in this circuit, you are wanted to behave in negative feedback. But because the feedback factor, the loop gain is so low, there is no negative feedback action in the circuit. Even if there is a negative feedback, that is really small. The feedback quantity is so small that you can treat it like this circuit is an open loop. The feedback quantity, whatever quantity is being fed back, is so small that I can treat this almost like 0. If this is 0, your signal passes through as it is multiplied by the gain. So A times Vi equals V0. Okay, it's almost like the system is an open loop. That's the problem with the circuit. So whenever you want to design, see what's happening here is that your beta is so small. Therefore, you thought that I would get 1 by beta. Ideally, you wanted to expect a gain of 10 power 6. You wanted a gain of 10 power 6 out of this non-inverting configuration. But to get a gain of 10 power 6, your forward path gain has to be much greater than that. Okay? So that you need this condition to be satisfied, right? Only the negative feedback will work. A beta should be much greater than 1, which means A should be much greater than 1 by beta. Your loop gain has to be much greater than 1. And this would imply your A has to be much greater than 10 power 6. Right? I'm ignoring the 1 here. So it's actually what, 10 power 6 plus 1. But since 1 is like 6 orders of magnitude lower, I'm ignoring 1. So beta can be treated as 10 power minus 6 directly. 1 by beta is 10 power 6. So your loop gain has to be at least much greater than 10 power 6. Okay, at least 2-3 orders of magnitude. So you should expect A beta to be at least, say, 1000. So which means your A has to be at least, here I've assumed the loop gain is at least 3 orders of magnitude greater than 1. You can even have 2 orders of magnitude. So A should be in the order of 10 power 8 or 10 power 9. For you to get this non-inverting amplifier to act like a non-inverting amplifier, meaning it should give you a gain of okay. So no, there is feedback, but so one of you asked a question: how did you arrive at the voltage 0 here when there is no feedback? See, think like this: there is feedback. If output voltage is V0, the quantity that is fed back is simply what? V0 into beta, which is 10 power minus 6 times V0. Okay, so V0 is getting attenuated by a factor of a million times, 10 power minus 6. It's a very small number. Okay, so that's why I'm saying that even though the quantity is being fed back, the feedback quantity is so small that I'm ignoring it. I'm not saying it is 0 exactly. I said you can treat it like no feedback. It is so small that I'm ignoring it. So since the voltage is so small, I've treated it to be equal to 0. That's it. Yeah. Okay. So whenever you want to design an amplifier with a gain of 10 power 6. Remember, that's what it's a very ambitious goal. In a single stage, you want to have a gain of 10 power 6. Okay. That's not possible because you are limited by the op-amp's gain. So if you were to really build an amplifier with a gain of 10 power 6, what would you do? You have to either pick an op-amp with a gain of 10 power 8. Okay, 10 power 8 in decibels turns out to be how much? 160 decibels. That's, yeah, That's again a very high gain to achieve very high gain. Many discrete products may not have this high a gain. So what would you do? If I want to achieve an overall gain of 10 power 6, I want to achieve a gain of 10, closed loop gain of 10 power 6. What should I do? I can simply cascade two stages with a gain of 10 power 3 or 10 square each. See, if you are given an amplifier with a gain of just 1000, okay, then what will you do is that you will just build one inverting amplifier with a gain of 100 each, because your forward path gain is 1000. And if I put a beta of 1 by 100, so let's keep it at, this is 99R and this is R, then your beta becomes 1 by 100. So 1 by beta is 100 for this stage. So A beta is at least 10, right? A beta is 10 cubed by 100 is at least 10. Cascade a similar structure like this. So cascade another amplifier and cascade another amplifier. So then if I cascade three such amplifiers, identical amplifiers, 99R and R and 99R, so then yes, I will get a gain of 10 power 6. Okay. But now what happens is that the variations in the first stage, if your gain is, let's say I want a gain which is insensitive to process variations. Okay. The variations in the first stage gets amplified by the gains of the next two stages. So you slightly lose out on the variations bit, but it is still, this is how you would go. If you just had a opamp with a gain of 60 decibel, which is 10 power 3, and you want to achieve a gain of 10 power 6, you cannot do that in a single stage. That's the point I'm trying to make it through this example. If you want to achieve a gain of 10 power 6 in a single stage, in a single differential, in a single inverting or non-inverting configurations, it's not possible. If you want to achieve that gain, then you need an open loop gain of at least 10 power 8 or 10 power 9. Okay. And that's a really large amount, 140, at least 140 dB plus, right? This is 160 and 180 decibels DC gains. So then if you, as a discrete designer, if you have to build it, then this is the easiest way to achieve very high gains. Okay. So that's something to keep in mind. So since we have studied the impact of, since we studied the non-ideality, which is DC gain, I'm just showing you an example where it actually has an impact. Okay. How do you see if you read the data of from the data sheet and you find that your DC gain is low, then in your mind, you should know that in a single stage, I cannot get very high gain out of it. So that's something to keep in mind. Okay. This problem, it's a non-inverting configuration with some offset nulling. What I want you to do is analyze. Okay. So one of you're asking, is that much gain? Do you need so high a gain? Do you need 10 power 6 as a voltage gain? I gave you some examples, right? Sometimes your sensors can generate microvolts of signals. And let's say you have to interface it to an ADC, which is operating in volts, maybe a few volts. Then you may have to amplify that, right? You will have to amplify that, and you'll have to amplify it to at least by 10 power 4 or 5 to bring it to volts level. So very, very niche applications where you have weak signals, which needs to be brought to volts for some digital, for example, the ADC might be sitting inside a microcontroller. And then you may have to put this before that. Okay. The important takeaway point that I'm trying to make here is that what I'm trying to say here is that if you have to build a very high gain in a single stage, okay, which means your beta has to be very low, right? If your beta is very low, then 1 by beta will be very high. All I'm saying is that if you want to realize a very high gain in a single stage amplifier, you need to have a really high gain, much higher gain for the opamp. Okay, the DC gain of the opamp has to be much greater than 1 by beta. That's all I'm trying to say here. This is something to keep in mind, because so far we didn't analyze the impact of DC gain in circuits. So I'm just showing you an example where DC gain matters. So as when you are realizing very high gain, it matters. Yeah. So let's now come back to this circuit. It's a inverting amplifier circuit with some offset nulling circuitry. Okay. What I want you to do is do a quick analysis. Assume you have input offset, input bias current present, and there is also input offset voltage. Both are present. Okay. Input offset voltage is present and bias currents are also present. So now if you have both of this, can you try solving this? Have both of this. You can treat them as three independent sources. IB plus, IB minus flowing through this, IB plus flowing into the positive terminal, and V offset presented. You can model V offset as a series voltage source in the positive terminal. Okay, so let me take this off. Yeah. Start one by one. First, you want to apply, assume only input is present. So here you have four sources of independent sources of noise. You can treat it like that. The input voltage, the base current, and the positive and negative terminals, the offset voltage, and there is also the potentiometer voltage. So let this node voltage be called as V pot, which is the variable voltage. So this node voltage is V pot, and that's a variable voltage. So you can assume there are 5 sources present here and analyze it one by one. So start with input. Assume every other quantity is 0. If every other quantity is 0, V pot is also 0, then your positive terminal will be at ground. Then it's a simple differential, inverting amplifier with a gain of minus of RF by R times Pi. Now, let's assume only one other source is present. Let's assume IB minus is present. IB minus. So again, if IB minus is present, I'm assuming V offset is 0, IB plus is 0. So no current is flowing in this node, and V offset is also 0. So which means, and V pot is also 0, right? I'm ignoring this node voltage as well. So again, I can treat this node voltage as at ground, and IB minus is a current flowing here. Input is also at ground. So that will flow through the feedback resistor, and the voltage drop across this will be IB minus times RF. Okay, so that will be plus IB minus times RF. Okay, it's a very simple circuit. The next step, once you have analyzed these two, start with IB minus. Only IB minus is, IB plus is present. If only IB plus is present, yeah, this is, I think, fine. Yeah. If only IB plus is present, what will be the voltage of due to IB plus at the output? See, you IB plus will see, if you assume V pot is 0, that is this node voltage is 0. If I assume this node voltage is 0, then you have R and 100R in parallel. I can approximate it to R itself, right? You have two resistors. The smaller of the two resistors will dictate the overall parallel resistance. So I can treat it as R, and the voltage at this node, because of IB plus, is going to be minus IB plus into R. Okay, minus IB plus into R will be the voltage at this point. That multiplied by 1 plus RF by R. That multiplied by 1 plus RF by R will be the output voltage due to this. Okay, so IB plus I have captured, IB minus I have captured. Next is the V offset voltage. If you want to capture V offset voltage, again you have to assume IB minus is 0. IB minus is 0. V offset, you can treat it like a voltage source in series with the input. Since there is no current flowing inside the op-amp, I can treat the voltage drop across these resistors to be 0. Okay. So then it's like V offset appearing at the positive terminal, which will get amplified as a non-inverting configuration. So that will be V offset times 1 plus RF by R. Finally, let's include V pot, V that is the potentiometer voltage. So if you include that, so I'm only showing this as V pot now, which is a variable voltage source. Okay, V pot can be treated as a variable voltage source, which you will vary using a potentiometer. Okay, potentiometer with the 3 terminals. So if you consider only V pot present, so then V pot undergoes a potential division here when you refer it to this positive terminal. So then that ratio is going to be V pot divided by 101 times. Now you have to, you are at this point. From here onwards, it's a, once you reached the non-inverting terminal, from there it's a non-inverting amplifier, right? 1 plus RF by R. 1 plus RF by R. That's it. So now you have the overall expression for offset with offset nulling circuitry, offset base currents and with non-offset nulling circuitry. So what you have here is RF by R times VI plus a host of other terms. And then these 3 are non-ideal terms. So these 3 are non-idealities. The sum of these 3 terms, okay, if you add these 3 terms, depending on the polarity of V offset and IB plus and IB minus, the sum of these 3 terms can be positive or can be negative. Okay, so that will be V non-ideal. So that will be, I can lump them all together and call it as a single voltage source as V non-ideal. So one of you were asking me, can I model V offset at the negative terminal? No, the impact should not be different. It should be same. The thing is that it just makes analysis gets complicated. We just see, the goal is that whenever you are modeling input offset voltage, it just means that the V plus and V minus are not exactly at the same voltage. Okay, they will not be. When the output goes to 0, your V plus and V minus are not exactly at the same voltage. So that has to be captured somehow. To do that, I can either put a voltage source at the positive terminal or at the negative terminal. Whenever you are analyzing circuits, always put it at that terminal where the analysis might become simpler. Okay. So far in all our analysis, we have been putting the offset always at the positive terminal because the analysis is much simpler there. That's it. You should get the same answer. The answer should not be different. Okay, let me make a point here. We'll discuss that later. So finally, you have these 3 terms. V pot by 101 times 1 plus RF by R. Now, all I need to do is choose this V pot to be equal to negative of V non-ideal, such that this whole term becomes equal to minus of V non-ideal. Then I can cancel this out fully. Right? These 2 terms will cancel out. So the point I'm trying to make here is that using an offset nulling circuitry, I can cancel out both the effects of base currents and offset voltage. Not just offset voltage, which because we introduced this concept of offset nulling and said that you can cancel out the offset. I'm trying to convince you here that this can be used not just to cancel off offset, but also the problem of bias currents. Okay, both the effects can be cancelled out. Okay. So